Hello, I'm Craig Parker from WIT's Planetary Health Research. Today we're exploring the convergence of artificial intelligence and climate science at the operational frontier. This is not theoretical research anymore. We're examining real-world deployments, transforming atmospheric prediction, biospheric measurement, and industrial mitigation across 2025 and 2026. The technological synthesis, machine learning, and climate science. We're examining global developments, operational frontiers, and strategic imperatives for 2025 to 2026. This is a strategic reading deck analyzing the current operational outlook. The convergence of AI and environmental science has matured. We are moving from theoretical projections to operational deployment across three critical domains. First, atmospheric prediction, transitioning from numerical weather models to neural Earth systems. Second, biospheric measurement, from manual allometry to multi-scale LiDAR and 3D modeling. Third, the technosphere, from passive reporting to active AI-driven process control and optimization. The AI environmental sustainability market is projected to reach $49.27 billion by 2030, with a compound annual growth rate of 14.58%. Industries are now demanding higher precision to meet stringent standards, such as the Inflation Reduction Act, methane fee, and EU regulations. Traditional numerical weather prediction relies on solving complex fluid dynamics equations, constrained by massive supercomputing resources with high latency and processing. The new standard is neural Earth systems, data-driven models offering kilometer-scale resolution and orders of magnitude faster execution. These systems can run on local hardware, providing resilience against infrastructure failure. Neural Earth systems reduce spin-up time, offering accurate forecasts in poorly gauged regions and superior performance on specific verification targets. Let's examine three breakthrough case studies. First, DLSIM from the University of Washington simulates 1,000 years in just 24 hours using a single processor with dual neural networks for atmosphere and ocean. It shows superior simulation of tropical cyclones and Indian summer monsoons versus traditional models. Second, Google DeepMind's GenCast and GraphCast outperformed the ECMWF operational ensemble on 99.8% of verification targets, delivering 10-day global forecasts in minutes. Third, ECMWF's own AI integrated forecasting system shows 10% better accuracy for large-scale patterns and 20% improvement in tropical cyclone tracks. Pure deep learning can be prone to confounding by chaotic noise and natural variability. The hybrid future lies in physics-informed neural networks, or PINs. These architectures enforce physical laws like thermodynamics and mass conservation within the learning process itself. This produces physically plausible output that anchors deep learning with physical process models. While machine learning improves performance, as seen in deep ACOPF models for power grids, rigorous benchmarking against linear baselines is required to ensure outputs adhere to the laws of thermodynamics. Traditional measurement in the biosphere relies on allometric models based on limited data, often fewer than 4,000 trees, leading to massive overcrediting in carbon markets. The solution is multi-scale LiDAR through initiatives like the Silvera Biomass Atlas. This involves $10 million in proprietary field campaigns scanning over 250,000 hectares. Terrestrial laser scanning creates 3D explicit models of individual trees, achieving 6 times more precision than conventional methods with error rates below 9%. A case study in Mozambique's Miombo woodlands revealed 1.5 to 2.2 times more carbon than previously modeled, enabling defensible credits for carbon markets. Baselines for wheat price forecasting. It correctly interpreted the 2020 soybean surge as driven by trade policy, not just climate. Second, in the Cryosphere, monitoring glacial dynamics. In Greenland, machine learning algorithms identified 552 glacial lake outburst floods between 1992 and 2020, compared to only 57 previously documented. In high mountain Asia, HRNet deep learning models automated the mapping of 597 rock glaciers. At the macro scale, we now have unprecedented methane surveillance infrastructure. MethaneSAT provides high-precision, free public data for accountability. GHGSat operates a fleet of 16 satellites by 2025, identifying methane plumes invisible to the naked eye. Climate Trace tracks PM2.5, plumes from 660 million sources globally. Satellite data reveals discrepancies between reported and measured plumes, exposing undercounting by landfill operators. Radical transparency is achieved via monthly data releases with only a 2-month lag, creating unavoidable accountability for emissions. At the microscale, lean burn natural gas engines are efficient, but prone to methane slip, unburned methane, surfan, escaping combustion. The AI intervention involves 2 components. First, dynamic optimization. Machine learning algorithms adjust air-fuel ratios and catalyst temperatures in real time based on operating conditions. Second, predictive maintenance, forecasting catalyst degradation from sintering and poisoning to schedule interventions before performance degrades. The key result is that AI-driven strategies align engine performance with US decarbonization goals and compliance with the Inflation Reduction Act. Subsurface intelligence is revolutionizing carbon capture, utilization, and storage, or CCUS, and enhanced oil recovery. The innovation is the smart proxy model using neural networks to optimize CO2 sequestration. This achieves an R-squared value of 0.9, replacing computationally expensive reservoir simulations with rapid proxy modeling. Using Latin hypercube sampling, the system evaluates 1,000 datasets for scenario optimization. The best performer is a moderate fluid type scenario with a net present value of $67.51 billion. The mechanism involves optimized water alternating gas, or WAG cycles, that prevent cap rock failure while maximizing storage capacity. The challenge in carbon capture material science is the high energy demands of capture processes and the cost of developing novel sorbents. The AI solution is inverse design combined with Bayesian optimization. This method identifies high-performing polyamine candidates and metal organic frameworks without exhaustive testing. Emerging breakthroughs from the University of Houston include membraneless EMAR technology, achieving over 90% CO2 removal at approximately $70 per ton, and dual-benefit flow batteries that provide both renewable energy storage and carbon capture. Results show improved CO2 selectivity by 15 to 25% compared to conventional screening methods. We must confront the environmental paradox of AI. The cost is substantial. Data centers will consume 1,050 terawatt hours by 2026. Training GPT-3 required 700,000 liters of water. However, the offset potential is significant. Sectoral efficiency savings from AI optimization in logistics, cement production, and building cooling could reduce global greenhouse gas emissions by 0.3 to 1.9% annually. PwC modeling suggests that if AI adoption scales correctly, efficiency gains in these sectors outweigh data center consumption. The net impact depends on creating enabling conditions, including policy alignment and a focus on computational efficiency. Corporate green compute initiatives are accelerating. Microsoft is targeting carbon negative operations by 2030, using mass timber data centers to reduce embodied carbon by 65%. Google's circular net model achieves over 90% waste sorting accuracy. Regulatory pressure is intensifying. In the USA, the Inflation Reduction Act methane fee is rising to $500 per ton in 2026. The EU has implemented strict methane emissions rules for fossil fuel imports. Geopolitically, we're seeing AI sovereignty emerge, with nations building domestic large language models and infrastructure to secure climate and industrial data independence. 3 strategic imperatives define the operational frontier for 2025 and 2026. First, hybridization and benchmarking. Resilient systems must anchor physical process models with deep learning. Rigorous benchmarking is required to distinguish true climate signals from noise. Second, radical transparency. The era of self-reporting is over. Multimodal monitoring, combining satellite data, IoT sensors, and AI, creates unavoidable accountability for emissions. Third, efficiency by design. We must move toward net positive AI. Specialized modular architectures must replace one-size-fits-all compute to ensure energy savings outweigh consumption. The hype phase has passed. We are now in a phase of intensive execution, characterized by high-precision monitoring and verifiable emissions reductions. The transition to a sustainable future is no longer about experimental pilots. It is about the technological synthesis, a deliberate fusion of machine learning speed and physical science rigor.